thing in this case, but I want to review that just a little bit. So first of all, before I say that, gamma as a function of a complex number has poles at z equals 0, minus 1, minus 2, all the negative integers. So one thing we can already see is that for d equals 4 dimensions, this is gamma of 0, and there's a pole. So in fact, through all the massaging, we have still got stuck with a divergence. Okay? But that's not good enough, because surely if I were doing 5-dimensional physics, if this was integral d to the 5th cube, this would be linearly divergent. So you might think, well, so somewhere here it should behave badly when d equals 5. But instead I get gamma of 2 minus 5 over 2, which is gamma of minus a half, which exists. Okay? So somehow you are cheating. This is not just some super slick evaluation and then you see for 4 dimensions you still have the divergence and everything's okay. We have really done something like in this process, and we have to spot where was the mistake made. Okay? Let me get it out. Let me get it out. Where is the mistake? Okay. I don't want to do it in this beta function thing, but maybe I should. Yeah, I find it a little bit painful to do it in terms of this beta function thing because it's a complicated function of gamma. But gamma, so the analogy, but this is only a very minor analogy. It's almost, what I'm about to say is the gamma function level, I really ought to have just said at the beta function level. Because the beta function is what comes up in that integral. The gamma function is like a baby beta function. I hope you see that, baby. But the gamma function has this simple, so gamma of z is equal to integral dy from 0 to infinity y to the z over 2 minus 1 e to the minus y. This is a representation of the gamma function. And one way to just check that it feels comfortable is the definition of the gamma function written as an integral form of the gamma function. If you chose z to be a positive integer, then no. If I choose z to be a positive integer, then you can check that by using integration by parts techniques, in other words, by knowing all the tricks of standard integration, which all of you know, that this is just z minus 1 factorial. Okay? You can do this integral for integer z, for positive integer z, and it's z minus 1 factorial. Okay, you know what I mean. But of course it makes sense. Well, let's see, when does it make sense? It makes sense as long as I can do this integral. So if the exponential will always allow me, things are always going to converge for large y. But for small y, this exponential becomes irrelevant. It just drops out to 1. And I could get in trouble if this z, the real part of the z, is too negative. Okay? So in fact I do. In fact that's where this first pole comes in. You can just check for yourself. Bad things happen when this z gets to whatever, 0. Okay? Because then it's integral dy over y. And at 0, I can't do the integral. Okay? If I'm very near it, I can do the integral, but then I'll see that I actually have a pole in z. So, integral representations might define a function, but not allow you to go outside of some region in which the integral makes sense. But of course, you can easily see that gamma of z plus 1 is equal to z gamma of z when these quantities are defined. Okay? That's something that just by using this representation, whenever it does make sense to talk about this, this is an easy thing to derive, and it's derived by integration by parts. Okay? So the brilliant idea of analytic continuation here is to simply say, I don't want to think about the function defined this way alone. I want to think about the function defined like this for positive z, or at least for the real part of z positive. And then I want to use this relationship to allow me to move it back. You see, another way to write it is, if I want to know what gamma of z is for negative, for z a little bit negative, I can just require this to be true, and it'll tell me the answer in terms of gamma of z positive, because a little bit negative z plus 1 is positive. And then I can use this to calculate what it is. Okay? So define gamma for real part of z negative using this relation. Okay? It allows you to recycle. So this is z. This is real z. It allows you to minus 1, minus 2, minus 3. It allows you to use, if you want to calculate, anywhere here, you want to calculate the gamma function, you just relate it to the behavior here using this property. And it automatically moves you back 1 and then moves you back.
But for negative integers, it's...
But for negative, but this thing, the z, but of course it's gamma of z over gamma of z plus 1 divided by z, right? Gamma of z equals gamma of z plus 1 divided by z. Which means, if you try to use it, for example, at z equals 0, it's still no hope. You're still stuck. You actually get the 1 over z pole. And in fact, play around with it yourself. You'll see that this way of trying to pull yourself back ever more defines a smooth analytic function everywhere in the whole entire complex plane, except these special places where you pick up this as a denominator and you get these poles. Okay? So what you're doing is you are taking the integral representation, generalizing it for fractional values, or complex values, and even then it's not well defined everywhere. And then you are using this property of analytic to define an analytic continuation and say, look, it's defined in a large enough patch of the complex plane. Analytic continuation tells me how to sort of define it everywhere. This is a trick for doing it for the gamma function. That's what's happening here. It's a function of integers, but then we see that, in fact, we can define it in the complex plane as some sort of integral representation of the number of dimensions. But this integral representation actually doesn't make sense. It does not converge for a large enough dimension. But it does for a small enough dimension. And therefore I can define it for all dimensions, except a very small number of discrete cases, by analytic continuation. That's what's going on at the end of the day in this whole procedure. We are getting an answer which is got some special places. Unfortunately, 4 dimensions is one of them. where there's just no trick in the book that's going to make a finite result. It's got a pole at d equals 4. But at d equals 5, or 4.3, or 4 plus 3i, it's all okay. The only thing I want you to get in terms of being a regulator is that the infrared part, that is, here, if I just didn't have to integrate to infinity, if I had to integrate to 10, you can put in, infinity here, sorry. If I put in 0.3, then this would be defined in the entire complex plan. We wouldn't have a problem if I could just start at 0.3. Okay? Similarly here, if I could just cap the integrals that I'm doing, whether I did it in 4 dimensions or slightly away from 4 dimensions, it wouldn't make any difference. The infrared part of these integrals is completely insensitive to a tiny change from 4 to something close to 4 in the complex plane. The only place it makes a big difference, all this voodoo that we're doing, is for the ultraviolet part of the Q integral, which is exactly the part that we mean when we talk about regulating the diagram. So next time, I will just take off from that point.
I thought you were about to explain why we don't see a blow up for d equals to 5.
Yeah, it's exactly, so all I'm saying is it's the beta function version of the following moral. This is like a baby version of a finite integral. See, it's an integral. Okay. And it depends on z, which you can think of as something like the number of dimensions. And you can see that this integral does not make sense for sufficiently negative z, in fact for negative z. But I can make sense of it by analytic continuation. So when you've written this formula down, you're secretly done that. Not only have you got the integral representation and saying, oh, it's an integral representation of a beta function. That beta function itself doesn't make sense for generic alpha and beta, except, in fact, it's a gamma function. The gamma functions don't make sense if you think of their integral form, except by analytic continuation. And you might say, gosh, analytic continuation, it's such an activist thing to do. You've gone and meddled with the real physics of it. You've meddled with the far ultraviolet. All I'm saying is that none of these moves have changed the integral from 0 to 10 in any big way. That is, whether I'm in 4 plus 0.001 dimensions or 4 dimensions, does not make any difference to the sort of the finite, the part of the integral up to energies comparable to the external kinematics. So I'm really doing a regularization. Okay. But there are 2 steps. One is the fractional nature of it, that is continuous dimension, but that was not enough. I did have to analytically continue. Okay, so look for the emails on when the next class is.
You sent it out, actually.
He already sent it out?
Yeah.
Oh, when is it?
It's 1:30 and 14:02.
Okay, so we have it.